that they know of the phenomenon that we're looking at. So those are the 8 steps, and we do those 8 steps for every demonstration in the sequence. And usually there's about 5 or 6 demonstrations that we do during one lecture class. Let me show you, I'll show you just one other related demonstration. It's the other one that's on your sheet, because this relates to asking if there's another analogous situation. The second demonstration asks, what happens if you have a ball and you toss it in the air? It moves upward, it reaches its highest point, and it comes back down again. What would the velocity and acceleration graphs look like? We can do that demonstration by putting the motion detector on the floor, taking a soccer ball and tossing it above the motion sensor, and the graphs that are collected look like this. And the students can see, because the shapes of these graphs are exactly the same as the shapes of the graphs for the cart, that they have actually discovered that there must be some sort of force in the laboratory. And this, of course, is what we call the gravitational force. Okay, so it's just another example of interactive lecture demonstrations. Okay, we do a lot of these in the introductory class when I teach it. And of course, the question is, do students learn concepts better from doing the force and motion interactive lecture demonstrations? And you can find the answer to that question in a paper that was published a while ago in the Physics Teacher. And you can download that paper using a link that has been put in the chat for you. So copy that link, and after this session is over, you can feel free to download that paper and look in it, and you'll find that there are examples of dramatic and robust learning gains based on students doing the force and motion interactive lecture demonstrations, with the testing being done by the force and motion conceptual evaluation. You might ask, do students learn from traditional demonstrations? Because surely ILDs are very different from traditional demonstrations. And the answer to that question is no. There's been research done that has shown that the majority of students who have seen a lecture demonstration in class but did not make a prediction about it or get engaged by it in any way could not even correctly describe the result of the experiment afterwards. So many of the most trusted lecture demonstrations that we do are actually too complex for students to learn very much from them, unfortunately. There is a book called Interactive Lecture Demonstrations. It's published by Wiley. It contains everything you need to do ILDs on 28 different topics, the prediction and result sheets, instructor's guides, teacher preparation notes to prepare you for doing them, and the 8-step process. And the book is actually free from Wiley, but I imagine that educators in India would have a difficult time getting it. So therefore, I've put a link in the chat, and you can use that link to download the entire book electronically. So please, again, copy that link from the chat, and after this session is over, feel free to get a copy of the book for free. And feel free to use these as much as you want. Why are these things effective? Well, when you ask students to make predictions, it requires them to consider their beliefs before they make observations of the physical world. When they see the difference between their predictions, which they've defended in their small groups, and the results that they observe, it causes a disequilibrium. And so it creates a learning opportunity for them. So students' knowledge is then constructed from observations of the physical world, and they are actually building their confidence as scientists because they're doing what scientists do. They're basing their knowledge, constructing their knowledge on their observations of the physical world. Okay, how can you incorporate ILDs into courses? Well, they can be used sorry? They can be used
Mr. Mr. Sokolov, you have been
Can you
muted.
hear me? Can you hear me now?
Now you're right.
Okay, good. You can also develop your own ILDs, but this, let me warn you that this is really not very easy to do. Oops. And one nice thing, there's no special classroom design needed for ILDs. You can do it in any lecture hall. And finally, let me say that on my course evaluations at the end of each term, the students say that ILDs are the thing they like most about the course. Okay, so now, having developed ILDs, roughly 4 years ago, the pandemic came along, and I decided that I would try to develop something that people could use virtually. And this is the origin of what I've called home-adapted ILDs. So let me talk about the design features of those. They're based on the in-class ILDs. They're also designed for learning concepts. They're anticipated as just one of a number of possible at-home components of a course. And they envision students working alone online. And the reason why they're for students working alone is because it takes a little bit of skill to be able to use breakout groups. And I thought at the time that I developed these that it would be better if it was the easiest possible thing to use. And instead of having live demonstrations, they make use of available multimedia. So videos, photos, graphs, and simulations for students to make their experimental observations. Now, hopefully this will be okay. I hope that most of you have a computer in front of you. I think you have to have a computer in front of you if you're watching me, so I guess I shouldn't worry about that. And you must have Wi-Fi. And in your chat is this link. This is the link to home adapted ILDs. You'll see that if I click on this link, it goes to this page. And this is the home adapted ILD page. And I'm gonna close this for the moment and just show you what it looks like. So here is what the page looks like. It has some background information. And then it has a list of 26 different home adapted ILDs. If you click on any one of those, it will take you to that particular ILD. Okay, so what I ask you to do is to click on the link that's in your chat and get to the home ILD page. Then click on the one called image formation. It's number 17. And when you click on it, there will be directions, and you will have probably more like 5 minutes to work. I just want you to get a feeling for what this is like. So individually, if you would go to the web page, open that ILD and work on it for about 5 minutes. I will be quiet. And in about 5 minutes, I will come back on again. You can download the prediction sheet and follow the directions. And this one happens to make use of a Physlet called image formation. So please go ahead and do that. And I will come back on in 5 minutes, which, let's see, that would be about 10:15 for you, 10:15 a.m. for you. So I will be back at 10:15. Okay, go ahead, please. I hope it works. Please tell me if it doesn't.
Sorry, Mr. Sokolov, I could not get the access of this.
Sorry?
How to get the access of image formation with lenses? This part
I'm
I'm not
sorry,
getting.
I can't understand what you're saying.
I'm not getting the access of image dot formation with lenses. This part.
Okay, I don't know why you're not getting access because there's no restriction on access. Is anybody else having that problem?
No.
Okay, a few more minutes. Okay, about one more minute, and then we'll move on to another one. Okay, so let's move on. And so I hope you had a little bit of time to play with that, but of course, after we're done here, you have free access to all of these. You can play with them all you want. But what I want to do is summarize the revised steps for the home adapted ILDs. So students download the prediction sheet. They read the description of the demonstration and they may view a photo, a sketch, or a video of the apparatus. They record their individual predictions on the prediction sheet. And this is a Word file that if you wanted to, you could ask them to send it to you to show that they actually did it. Then only after recording their predictions, the students observe the demonstration as a video, photo, or simulation, and they see the results. And then they describe the result on the prediction sheet. They compare it with their predictions, and they're often asked probing questions that guide their critical thinking about the results. And again, this procedure is followed for each of the short demonstrations on the prediction sheet in that a particular sequence. Okay, what I'd like to do is have you try one other, and this one is called Force and Motion, Newton's third law. And again, I'll give you 4 or 5 minutes. So again, go to the web page, click on number 4, Force and Motion, Newton's third law, because this one is a little bit different than the other one. This one uses videos. So play around with this for about 5 minutes or so. And then we'll come back and we'll talk a little bit more about home adapted ILDs, and then I'll give you a chance to ask questions. The link that you put there is not the right one, by the way. The one for someone posted the link and it's for the wrong. It's okay. Don't worry about it. Okay, a couple more minutes. Okay, so let me just say a few more remarks about home adapted ILDs. I hope you were able to get them to work okay. Um, whoops. So one important thing, they incorporate prediction, observation, and comparison, the same strategies that are used in in-class ILDs. I think one important point, since these 26 sets of ILDs are online and you have free access to them, if you wanted to do in-class ILDs and you had no equipment at all, you could do them using these resources that I've put there. That wasn't my intent in developing them, but I realized afterwards that all these things are now available. This is especially useful for secondary teachers. I know secondary teachers in the US generally have no equipment to use, unfortunately. Um, and this is an active learning strategy that new teachers can use immediately because once they get the idea of how to do it, again, they don't need any equipment. They don't need anything but the website to use and to understand the steps that are involved in doing them. I should warn you, they have not been research validated. I had no opportunity to do that. But if you wanted to do a research study with some of them to see whether they are effective or not, I welcome you to do it. I'd be happy to help you do that. And they're free. They're online. I hope that the majority of you, in fact, I hope that all of you have no trouble accessing them. If you have problems accessing them, please let me know and I'll see if I can fix it. But they're up there. They're on the server at the University of Oregon, and they're free to use as much as you want for as many students as you want. And I'm happy to help in any way if you're interested in using either in-class ILDs or home adapted ILDs. So at this point, I think I will wrap up what I'm going to say. I thank you for your attention. And this is my son, a photo of my son. It's actually a number of years ago. But I urge you to engage your students in the learning process. And now, if we can unmute people. I welcome any questions. First, I'm going to stop sharing. And so, are there any questions? Hello, anybody there? There. Okay.
Hello,
Yes.
sir. I'm actually a physics teacher from Doom School, Dehradun. I have attended your lecture live also in AAPT conference way back many years back when I was there in Georgia. So I intended to use it, but I got carried away by the hectic schedule. So now this time we have 2 months of vacation. I am planning to use it. So I want to take your offer of the guidance on the research paper. So I want to see how do you have any like guidelines on how I can conduct the research on the effectiveness of these, because I plan to use them for my classes from the new term.
Uh-huh. I'm sorry, I have difficulty understanding. There's
Okay.
something wrong
I,
with the.
I plan to use your resources once my school reopens in July. So I want to make a research paper out of the learning outcomes. So do you have any suggestions on how to plan my research?
How to plan, you're talking about a research project with these ILDs?
Yes.
Okay, well, probably we should consult between the two of us. But the type of research that we've done, as you will see, if you look at, you should look at the article in the physics teacher, is that we develop conceptual evaluations. So I anticipate that if somebody wants to do research, they will use those conceptual evaluations to assess student learning with pre and post tests using some subset of these ILDs. But let's talk. You have my email. You can email me and we can discuss it.
Okay. Thank you so much.
Sure. Anyone else? Can anybody share their experience? I don't know. Of course, I have no idea whether you were even able to use them because I can't see what you're doing. So can somebody share how it went
May I come in?
or what you thought about them?
May I
Yes.
come in, Professor Sokolov?
Yes, please.
Yeah, thank you. I think it was a very interesting lecture. The new element which we saw in it was asking the participants to make predictions. I think that is something very interesting because that is where I think all the what you call learning gaps actually start appearing and seeing that whether they have understood it or not. Please tell me one thing more. Before giving these demonstrations, do you really teach also this topic in advance to the students, or they are asked to uh, come ready in the class after reading some resource which you have provided to them?
It depends on the topic. There are some topics where an ILD, a set of ILDs could very easily be used to introduce a concept for the first time. And there are others where if they haven't heard anything about it, it's hard to do that. So for example, electric circuits. Students have many ideas about electric circuits that are not correct. But if they've never heard the terms current and voltage and power at all, then it would be very difficult to design an ILD that to help them understand the relationship between those concepts when they don't even know what they are. So in the case of electric circuits, we always do some other stuff on electric circuits before we do the ILDs. The ILDs are really used to clarify the concepts. In mechanics, many of the ILDs can be used to introduce things. In fact, the very first thing we do in mechanics is have students walk in front of a motion sensor. So they're creating graphs of their own motion. And that's how they're introduced to representing motion with graphs. So yeah, it depends on what the topic is, really.
Secondly, were you using some kind of a tracker software at the back end with the detector so that they can immediately see the graphs on the screen?
Yeah, yes, that's exactly right. I mean, they walk in front of a motion sensor and display their graphs as they're walking. Or they move a card in front of a motion sensor and display the graph as they're doing that. That's the idea.
Okay. There is another thing which I observed in that question on lens images, formation of images by lenses, that the lens which you had given was a plano-convex lens. I hope I'm remembering it correctly. And then you asked that please draw as many rays of light you can draw to map the image after passing through the lens. So even if you remove that plano-convex lens and represent it by a line, and you could have asked them that, look, you had put focal length also on the axis. That could have been enough to draw the image, even without that lens sitting in between. Was that plano-convex lens was a deliberate effort, or there was some motivation behind it also?
Okay, I'm not sure I understand.
See, that image which we were seeing, there was a plano-convex lens which was there. Now, if we see, there was another marking on the x-axis of the focal point, the distance of the focal point from the optical center of the lens. I am saying that even if we had removed the lens, and if we had represented it by a line and asked students to draw rays treating that line as a lens, which is that of a convex lens, they would have got the same results, isn't it?
Well, I don't understand why you would want to do that, because anytime that we make a representation of something that doesn't actually look like what the physical situation is, it doesn't help students. They just get more confused. So even though, of course, the lens that we use does not actually look like the lens that's on the prediction sheet exactly, because it's a thick lens. Here's the thing with ILDs, we are generally trying to get at something quite dramatic that students clearly don't understand. And so, for example, with the lens, the thing that students don't understand about a lens, I mean, actually, they don't understand anything about a lens. They don't understand that every ray that leaves a point on the object, that if you have a perfect lens, all of those rays have to end up at the same point on the image. In other words, and that there's an infinite number of rays. They think about, oh, maybe there are 2 rays. So we're even though the representation may not be perfect, they are so clueless as to what a lens does, and it's so dramatic when they see that it works. That's, there's quite a bit of evidence. I've done quite a bit of research on image formation and found that students universally learn from that set of demonstrations. because it changes their entire viewpoint of what a lens does, and that's what we're trying to do. So anyway, does that answer your question? I'm not sure.
Yeah, I think it's making a lot of sense. Yes, thank you.
You're welcome. Anybody else?
Any participant would like to ask a direct question? I think it was very wonderful and very great idea to have such home adapted ILDs.
Well,
I wish I would have known when I was teaching in college. It's
well,
really a wonderful tool. Yeah.
I wish I would have known when I was teaching also.
Yeah. It's really a great tool, for getting your concepts clear. Okay. But what do you think that if you just work with these, of course, the concepts would get clear, but what about the importance of hands-on experiments related to these concepts? Can students, I mean, if the student think that they can get away without doing experiments, is it advisable or?
Well, they're still making observations of the physical world in a sense. And I mean, it's not when they do simulations, they're not, but in doing ILDs, they are. And I have to say that when Ron Thornton and I first did ILDs in class ones, we were amazed at the learning gains that those produced. Because I agree with you, for up until that time, our focus was on developing active learning experiments for the laboratory. And we found that if you developed good experiments and a strategy for using them, that you could change students' understandings very, very dramatically. Oops, excuse me just a second.
Yeah.
So I think the important point is that they are making observations of the physical world, and therefore, but just in a different way. They're not doing the experiments themselves, but we are engaging them in the experiment. They're not just sitting there and watching something without being engaged by it. Okay, the thing about doing hands-on is that if it's done well, they're engaged by it. They're actually actively involved in it. So if you do a lecture demonstration in the same way, it appears that you can bring about a dramatic change in their understanding.
True. Yeah, thank you so much.
Okay, sure.
Yeah. Let me check the chat if we have anything. No, I think we just have comments. Nice presentation, Dr. Sokolov. Your ideas will help the future generation a lot. Thank you very much. There are many participants who have messaged as it was a very great presentation, really good, excellent. But I don't find any. I think people now would like to try the links which you have already shared with us and try those concepts, I think. Isn't
Sure.
it?
Well, I'm sorry
Yeah.
it was very rushed, but like I said,
No.
from now on, everybody has as much time as they want to look at those.
Yes,
So
yes.
to show what they were.
I think
Okay.
getting introduced to these things was a very, important thing of this today's session. And once I think we go on those links, it's unlimited thing that we are going to get. Yeah.
Okay, great.
Over to you, Swapna. Anything you please propose the vote of thanks. I'm on my personal behalf, and on IPT, on behalf of IPT, Professor David, I would like to extend a very heartfelt thanks to you, and looking forward to be associated with us in future also. So IPT is going to be enriched by your cooperation in future also. Thank you so much, and thank you for joining. Over to you, Sapna. I think Aluwalia sir has raised his hand. Professor Aluwalia, please come in.
Yeah,
You're very welcome, and I hope that I will hear from some people that they've tried to use them and hear about their experiences. So I
Yes.
put my email in the chat, and feel free to contact me at any time.
So
Yeah.
thank you, Professor Sokolov, for this wonderful interaction. I think we should, in future, whenever we have you, we will be more prepared. I think this time it was a kind of a trial where you tried to engage us also, and maybe we were not that much prepared. Maybe in future we will be better prepared. Second thing which I would like you to thank you is that Gyaneshwaran actually has made an offer to work on this as a research project itself. And let me just tell you that Gyaneshwaran has been a coordinator of Indian Young Faces Tournament in India. And he conducted one wonderful program last year. And we had lots of interaction with young students in that particular program. So I feel that Gyaneshwaran is just ready to take off as far as the research idea is concerned. And I'm sure that more IAPT members may join him in trying to do various other experiments in your web page, which are available, and do something meaningful with that, with the students as well as from research point of view. So thank you very much.
You're
And
welcome. I look forward to it.
and Professor Grover is also here. He is also a member of C14. Professor Grover, would you like to say something? Professor Grover, am I audible? Okay, all right. I think that's it, what I wanted to say. Thanks.
Okay. All right. Well, thank you for the invitation.
Oh, thank you, Professor
Look forward to
Sokolov.
hearing. Yep, you're welcome.
So let me give a formal thank you to everyone. So thank you very much, Professor Sokolov, for such a wonderful talk on ILDs and their profound impact on improving learning in introductory physics lectures, whether we are in person or virtually. So surely we are going to use them, and I am going to use them and revert back to you. So your presentation has shown us the immense potential of ILD as a research validated tool for engaging students and for fostering deeper understanding to them. So I'm also thankful to you for sharing all the links with us, the links of all the resources. So we are grateful to you for your time and effort you have invested in delivering this talk. So on behalf of everyone present here, I extend my sincerest thanks to you. So we look forward to continuing to be inspired by this and having more talks of yours in future. So thank you very much, everyone, for joining us today. Hope to see you soon with Professor David Sokolov again.
Thank you.
Thank you, sir.
Sapna.
And thank you, Rekha ma'am. Thank you,
Thank
all
you.
the dignitaries. Thank you.
Yes.
So with this, we come to the end of this session. See you again.
Yes.
Okay.
So
You're very
can
welcome.
we, yeah. So
Okay.
thank you. Thank you. So can we close?